right, thank you, Jesse, for the very nice introduction, and thank you for helping set up this tech talk. So what I want to convince you today by the end of this talk is the importance of transport questions model in MHD simulations, and especially for our application here, which is waveguides. So what you want is to develop accurate fluid tools that can be predictive in modeling dynamics of capillary filled waveguide. So there are a lot of contributors to this work here at RadiaSoft, but also our collaborators at the University of Rochester at the Flash Center that help us implementing models into the Flash hydrocode. All right, so here's a brief outline of my talk. I will quickly go over our application, which is the plasma-based actuators, and why we're interested in plasma-based acceleration. Then I will talk about the modeling aspect of waveguides. So our approach here is to use MHD. I will talk about the derivation of MHD very quickly. Then I will talk in detail about the transport coefficients model. These are questions that we put into our hydrocode. And my goal, as I said, is to show you how they can impact the physics or the dynamics in terms of temperature, transport, or magnetic field advection inside a capillary. I will show two test problems. One is for low Z elements that's a hydrogen, and we also do. I will also show result for an argon capillary. All right, so why I'm seeing this? All right, so electron beams are used in a wide variety of applications. In medicine, for example, they're used in high energy physics. This is a picture of LHC, the Large Hadron Collider over there in Geneva. Electron beams are also used, for example, in neutron generators as a way to do non-destructive screening. So they have a large and wide variety of applications. What we are interested recently, I mean, a couple of years ago, Tajima proposed this idea of using laser-based plasma as a compact accelerators. And the reason is plasma-based accelerator can produce high electric gradient, so up to a couple of hundred of giga-electron volt per meter in terms of electron energy. And so this is higher than what you could get from standard colliders, which are about a few MeV per meter. Nowadays, capillary waveguides are used to generate this very nice density profile that now can be used to propagate very intense laser beam generating electron beam that are, for example, here in the plot here in the middle, that are very energetic at about 1 giga-electron volt here with very few energy spread. So in this experiment, a capillary filled with hydrogen was ionized, and then a terawatt laser was used to propagate through that low density plasma and to generate very nice beam. Now, nowadays people are using larger, even because in that experiment the diameter was about 4,800 or about 400 micron. Right now, people are generating larger capillary, for example, up to centimeter scale. And so what we would like is to develop tools that can help in designing and analyzing experimental data. And so basically the requirement that we have here is to be able to run centimeter scale channels, and we want also to run these up to a few hundred nanoseconds. These time scale are quite difficult to model with kinetic codes. Kinetic codes were often used to do transport and to look at field advections but they cannot reach really this scale. And MHD is really the perfect tool for this type of physics. Additionally, MHD has a long history of being used to model gas discharges, for example, in Z-pinch or in tokamaks in the context of magnetic confinement fusion. So that's our tool. Now, what I would like to talk about really quickly is what is MHD. So MHD is a fluid description of long wavelength, long frequency plasma behavior. So one way to derive this is similarly what you would do is you start from a kinetic description of your electrons. You follow them in phase space by following the particle distribution function. You can write it in this way. So you have these advection terms, then you have the Lorentz force that describe the long range forces, and then you have an operator really on the right-hand side that describe the short-range forces, basically the collisions between the different entities that you have in your plasma. And this can now be coupled to the Maxwell's equations to describe electric and magnetic fields. Now, this is a closed set of equations, though you can solve it in different ways. You can either do pick, or you can solve it in a kinetic code once you choose an operator. So operator can be 0, that's Vlasov, or a Vlasov or Fokker-Planck with a more complex operator. Now, in MHD, we make this approximation, which is to say, we assume that the phase velocity of the electromagnetic waves are smaller than the speed of light. So we basically are in the limit of c going to infinity. So what that means is you can neglect this term here in this equation. And the second approximation is to assume that you have quasi-neutrality in your system. So basically, the electric field will adjust itself to make sure that the electrons and ion density are exactly the same time the ionization. So now that doesn't mean the electric field is 0, or even the divergence of the electric field is 0, but it means it will always change or adjust. Okay, so from here, once you make this approximation, in order to get to the MHD set of equations, you just take the velocity moments of this equation, and what that does is it gives you a set of conservative equations that tells you that your fluid, how the fluid is conserved, that the conservation of density, conservation of momentum. The last one is the conservation of the energy in your plasma. Now, this is a one fluid MHD model. You can drive the set for a two fluid, MHD when you have electron and ion separate. And now these are now coupled to the induction equations that tells you about the magnetic fields. Okay, now what we are interested here for our application, the waveguide, there's two physical phenomena. One is Joule heating, and the other one is about heat conduction. So you heat the plasma, and the plasma is also expanded, is so moved to the wall. And so the two physical phenomena that we are interested in are resistive heating and heat conduction. Those terms are in color here, so you need to know resistivity. We need to know a model for the heat conduction. Additionally, I put the electric field because the electric field is not known, so you need to have a model. And generally in MHD, you have to find a generalized home. So a way to find that is just by neglecting electron velocity. So electron inertia is neglected, then you end up with a generalized home for the electric field. Okay, so now let's look at the heat flux. So the heat flux formulation, we can look at the formulation from Braginsky, which basically show how the heat flux depends on the different transport coefficients. So you have the perpendicular coefficients here, that act to reduce heat flux. The cross act to deflect heat flux, and then you can see how these the difference between the parallel and perpendicular also impact the heat flux in your plasma. So for an anisotropic system, when magnetic field, when you think the chi, the magnetic field is important enough, the amplitude of these different coefficients will have a huge impact in the way energy is exchanged or transported. So I also put here the generalized home for the electric field, so which is written as the usual term here. This is just the Lorentz force, and the usual J cross B. The pressure gradient also generates fields in the plasma, so that is accounted for. The term that we are really interested here is the resistivity contribution to the electric field, and so this is a tensor. So you have these different component parallel perpendicular, and the same as for the heat flux. So here, if you want to know how a plasma inside a waveguide evolved, we need to know, we need to have accurate model for each of these different entities. And so the way we do that is through kinetic theory. All right, so once you have the generalized Hom law, you can put that into the induction equation, and you can rewrite it in a way that will that can give you insight into the impact of the transport coefficient in how they affect the advection of magnetic field, for example. So this is just induction equation. The time derivative, say this term is just the advection, how fields is advected. And this term here is a more complicated one. It just tells you the impact of resistivity gradients in generating fields. Now, the important term here that I want to discuss is this effective velocity. So you can write it in terms of the fluid velocity, and then you have the current, and then you have the J cross B term. So these are so what I want to show you here is what happened when you neglect these three different terms, the terms in red. So you don't have this J cross B, and you just go back to having the fluid being advected with the normal fluid velocity. And so that would be the ideal MHD. And so what you can see here, adding these terms, what they would do is they tend to alter inhibition or advection of the magnetic fields. So as you can see, being able to accurately describe heat conduction and transport coefficients is crucial in order to have a predictive capability. And finally, I would like to also mention like this recent study that was done with the Hydra, which is another MHD code at Livermore, where they look at in a whole room, we looked at the gold capsule, and so they neglect some of the MHD terms and just try to see how they impact. And the results show that there is a significant change in the temperature profile depending on the terms in the MHD that you neglect. So basically, if you neglect all the different coefficients that generate fields, the self-generate fields in the plasma, you tend to have very different temperature profiles compared to a full MHD description. So again, I hope I convinced you so far that these terms are important for MHD for MHD simulations, and again, the thing I think I haven't mentioned yet is the different coefficients are function of your material properties, so of your ionization, but also in how particle collide, the collisions. So that's what chi here is, basically the cyclotronic frequency time, the electron ion relaxation time, and so that has so all this physics is quite complex, but I think this make it a bit clear about how they impact the physics. All right. So now that we we think we know that this transport or questions are important for our physics that we want to look into. Let me show a bit brief description of existing transport model, or one of the most popular ones. So this is an old field, but recently renewed by the discovery of the Davies and Haines group. That most of this transport that we had, they are really smooth. When you put them in some hydrocode, you may get into like some instabilities and numerical instability that may give you non-physical results. So Spitzer harm is one of the oldest model. It was proposed for Lawrence gas, fully ionized system, no electron-electron interactions, ion are just a background, and you know it doesn't include magnetic field, so it's only for isotropic plasma. The most popular model that has been included in a lot of MSG code, including the argon code, is the Epperlein in Haines. So this model was derived by just correctly solving the Laserbased electron equation and fit the data to some numerical expression for 15 elements, and these have been used for a very long time in MSG codes and interpolate for different elements or element in the between. Recently, Davies at Rochester and some of their colleagues at Los Alamos National Lab have proposed a new and more accurate set of equation of state that solves some of the inaccuracies that Epperlein and Haines have, and they provide fits for basically an arbitrary number of Z of material and for an arbitrary magnetization. Now, what they did was something very nice. You've heard probably of the Braginsky model. Braginsky also used a Lager expansion of the velocity distribution function and Max in the Vlasov-Fokker-Planck equation, but it just stopped at the first term of the approximation. So Braginsky's are not quite accurate, and the Braginsky model was for four atomic number. All right, so let me show you very quickly some tests between the different models before we put them into our hydrocode. So this is the perpendicular component of the resistivity as function of chi. Chi is just the magnetization of the plasma. So for some of you who are in the laser-based in the laser accelerator community, you are providing this regime. It's very, very low chi for denser plasma, and with higher field, you are in this regime. So what you can see is Braginsky is quite bad in terms of prediction of the normalized resistivity, perpendicular resistivity. Epperlein and Haines and the new fits from Davies and his collaborators follow accurately. So, but there's a little difference here, but I don't believe that's very impactful. Now, if you look at the cross, which, as I showed before, participate in deflecting fields, heat flux, sorry, you still see similar agreement or close enough at low chi. Braginsky is still quite inaccurate. Now, when you look at the difference, which is also does get into the heat flux and the energy transport equation, you can see at low chi, which is the regime that again we are interested in for this application, it is really more than 20% difference in between all the different models. Now, the new fits were also validated against against kinetic tests. So we have strong confidence in the green one. So the green one does predict a lower resistivity. Now, when we look at the conductivity, I put Spitzer there as a reference. It's sort of unfair to Spitzer to put them here because they were not developed for anisotropic systems. But it's good for just a reference, because most of these models should go, they should asymptotic to Spitzer at when the magnetic field is 0. So again, Grumman is not that bad. Braginski was underestimate here a bit, but they are close enough. Now, Spitzer for an isotropic plasma should not be used, of course. I think everyone knows that. Now, G-held for the cross one, G-held and Epperlein and Haines agrees well. So the perpendicular and the cross for the conductivity, the new models do agree quite well with the previous model of Epperlein and Haines, but not with Braginski or Spitzer. Now, this is another important point that we want to make, which is the cross one. For the cross one, though, which is in the regime that we are, we saw this discontinuity in the Epperlein and Haines models, which is also, and people at the Salmos and Livermore have also foreseen this in their tokamak simulations, and especially at loci. So if you do any simulation in laser-based actuators, you should not really use Braginski, and the new fits from G and Hell and Davies are quite accurate. All right, so we put these tools into the Flash code. The Flash is a radiation MHD code from the Flash Center, which is now at Rochester in LLE. So the code is designed to model plasma physics and astrophysics. Right now, we're solving the standard Euler equations on the block structure. It has a capability to do pre-temperature. So for our plasma, we are very low density. So particles, electron and ion, really do not equilibrate at the same temperature. So you can, the code allows this option to have an energy equation for each of the different particles or entities, electron, ion, and even the radiation. Transport coefficient model, we have different options in the code, and we've added these new transport coefficients. In terms of equation of state, you have the option of either using ideal gas, which is quite fast, or if your system is more complicated, you can the code does accept tables, equation of state tables, and we've been working on building equation of state using QoS and other more complex equation of state. In terms of energy deposition, you have a laser deposition that rely on inverse Bremsstrahlung. So, and it uses a laser tracer. So this can be quite expensive sometimes, but it's very accurate. In terms of electron ion relaxation, so it had different models. You can use Spitzer model. They also have the Lee and Moore model that's quite good for dense plasma. In terms of MHD, unsplit target mesh, second order predictive corrector. So if you want to access the code in no more detail, that's a reference for the Flash Center. Let's go check it. So back to our capillary simulations. So we used embedded boundary capillary representation. So the figure here at the left show what our capillary looks like. So the wall composed of, we represent explicitly using alumina. So they are part of the domain. Thermal conductivity and magnetic fields are computed self-consistently across boundary. And magnetic fields is applied right at the capillary wall here at 250 for this. And the boundary is fixed. It's described as a fluid, but it has zero velocity. In terms of discharge, we have different options. So the discharge is represented by a magnetic field at the capillary. So we use Ampere laws to specify the electric fields. The magnetic fields that we estimate through the current, and that electric current is the magnetic field is then is then used to heat the plasma, basically. So we have different options here. That what the plot on my right show. So you can either use this linearized simple one or sinusoidal. The code, we build tools in the code so that it can also take experimental file that of current that was produced from experiment, which will give results that we hope is closer to the experimental data. Okay, so I just would like to go quickly through the different stage of the dynamic in the capillary. And so I talk about the initial phase, the breakdown by applying this discharge, we ionize. So the discharge is applied through the magnetic fields. The magnetic field penetrates plasma, heat it, and ionize the gas. And that phase persists until full ionization. For the case of hydrogen, that's this step may take 100 nanoseconds or less. For high Z, I don't know, helium or argon, it may need a high charge. So the temperature, so once that after that phase, you have a new phase start where you have a hot inside the channel. It's a hot. The wall are very cold. So so thermal conduction move the heat towards the wall. And what that does is basically you have these two physical phenomena, that Joule heating, heat conduction, they balance each other, and that creates this steady state and generate this very nice, for an ideal capillary, it's very nice parabolic profile in green that can be used to accelerate or to guide an intense laser beam. And so for most application fields, density profile are critical figure of merit that people use as diagnostics. And so that's the other importance of using MHD, because you naturally access these macroscopic information. All right, so we put this code into these different models, some of them into our code, into Flash, and run some simulation for hydrogen and for argon. And so this is one of the first results where so here I'm plotting the temperature and the channel function of R, the radial coordinate, at 100 nanoseconds for different models. So the first here in blue is the Spitzer model. I have a plot of Davies and collaborators. So that's what we call here the new models. And then you have the Epperlein model. And so what you can see here is there almost a 2 EV deviation in the channel. And also note that the Spitzer model generated the channel around 10 nanoseconds more quickly than the Epperlein model. So again, these rates, you can tell you how fast or energy is being moved or depleted from the channel to the wall. So you can see if there's difference in terms of these models, they will have an impact at how fast or slow the channel is being built. Now, if you look at the magnetic field, surprisingly, Spitzer is quite good in predicting the magnetic fields. So here but the Epperlein in hand predict a lower field in the channel and also at the wall. So we run a different test case for an argon test, for an argon capillary. So, and here we compare the two models, Epperlein and Haines, and the new fits that we think are quite accurate and cover a large parameter space range. And so what you can see on the left is a temperature at different time. So the difference of estimation of Spitzer of Epperlein and Haines like still holds even at different time. It doesn't change. The peak still holds. So like here you have about 1 EV. but when you look at the azimuthal magnetic field, you see the opposite, which is it underestimates the magnetic field. Now, the difference is not quite significant, but this is still at 300 eV and for argon. Now, we did this for argon because argon capillaries are leveraged for different applications because the higher mass can inhibit channel formation. Right, so I'd like to conclude here. So we've used new transport model fit for anisotropic plasma in the Flash code to simulate gas-filled capillaries. So we've been working with Flash for a couple of years now and building a lot of new tools to model capillary discharge waveguides. Our simulation found that temperature profiles are very sensitive to transport coefficients model. While Epperlein and Haines predicts a higher temperature, the difference in magnetic field is less significant. So we're also working adding new physics in our configuration. For example, equation of state. We're using this radiative collisional Flash code that has a better average ionization model. My colleague Stephen Coleman has been also working on the 3D Cartesian geometry simulations. For our simulation so far, we haven't addressed the 2D. We haven't looked into the Berman battery effects and the cross gradient. So these are terms in the induction equation, and they can result in additional magnetic fields in the plasma. For our configuration, we think they may not impact. They don't have an impact for the setting, but for 3D geometry, they may have an impact. So these are something that we are thinking also of looking into in the future. Thank you all for listening.
All right, thanks, Abdu. That was excellent. I'll just remind everyone, you can drop your questions into the Q&A and we'll address those as they populate. We do have a couple that are waiting in line to start off with. So if you're ready, Abdu, I'll just go ahead and read these to you. First question in line is, do the new coefficients fits show new physics that the Spitzer model is missing?
Yeah, so that's a good point. I mean, so far what we show is something that is very similar to what other studies have shown using this new fit, which is there is not a big difference in terms of magnetic fields, but in terms of temperature, these descriptions do predict a lower temperature and a formation of the channel, let's say 10 times later, 10 nanosecond later than the Spitzer model, the Spitzer model, or the Epperlein and Haines model. So physics is quite similar, but there is a delay in terms of the time, the formation of the channel, and there is a difference in the amplitude in terms of the temperature. For the magnetic field, physics is amplitude is quite similar, but there's still differences.
Thank you. And then there's a follow-up question to that. Will these effects wash out at later times or sustain?
Well, that's a good point. And so for the hydrogen case, we ran it up to a very long time and did not see big changes. I don't know what would happen for the argon case. So I would say the difference seemed to remain even at a later time. Here at 100 nanosecond, we seem to still see the same difference in terms of amplitude to not change at all.
All right, thank you. We are just a couple minutes over time, so we'll do one more. Question coming in. Do you compare your results with the results obtained in NPinch and Marple codes?
Well, that's a really good point. And I think and it's something I really want to do, to have this code composition test. So we've started to work with, I think, a group at DESI to validate our settings. But yes, that's something I haven't done, but I will be working on just making sure that we. I mean, I look at Marple, and the paper I've seen are mostly they have a 2 fluid code basically. So the electron, and here we have a 1 fluid, and I'm not entirely sure how we could have a 1-to-1 test between those codes. But either way, I think that's a good point, and we'll be working on doing those tests.
Awesome, thank you. And then one quick little question here right before we wrap up. Will these new models be available in Flash code, or are they already available in Flash code?
Well, so I think in the next release, because some of these models were already implemented by our collaborators over there at Flash, Eddie Hansen. So I think they will release it. I don't know the timeline on that. So
I can maybe jump in on this too. Yeah, I think that the Davies 1 anisotropic models should make it, at least for the resistivities, into the next Flash release. I don't think there's any plans to implement the additional components of the Epperlein Haines model, which we implemented for this study. But I do think that the Davies 1 et al. Models for the resistivity, at the very least, will be in the next Flash release.
Awesome, thank you. That is Dr. Nathan Cook, who's one of our senior research scientists and collaborates with Dr. Diaw on some of these projects. So, that's what we have for today. We're at 12:40, so we're going to need to check out. But thank you, everybody, for showing up. We will be offering a recording of this webinar on our YouTube channel coming up next week. So we will send you a link to that when it populates. Thanks, everyone, and we'll see you next time.
thank you all. Thank you, Jesse.
Thanks, Dr. Diaw.